Welcome to the first video of the last of the APES units. This short video is going to cover two ozone-related topics: 9.1, stratospheric ozone depletion, and 9.2, reducing ozone depletion. Ozone is a molecule comprised of three oxygen atoms, O3. Depending on where ozone is found in the atmosphere, it can either be beneficial or detrimental. In the troposphere, the lowest layer of the atmosphere where we exist, we already know it to be a pollutant that causes respiratory irritation and harm and can also damage plant tissues. But when it's in the stratosphere, it provides for the protection of life on Earth as we know it. In order to understand how ozone functions, we first need to take a look at the relationship between ozone and ultraviolet radiation. Our sun produces a variety of electromagnetic radiation, including, but not limited to, the visible light that we can see, red, orange, yellow, green, blue, and violet, the infrared radiation that we feel as heat, and ultraviolet radiation. Visible light occupies this range of wavelengths, from 400 to about 750 nanometers. Beyond 750 nanometers is where infrared radiation exists on the spectrum, and below 400 nanometers is where the ultraviolet radiation is. In this spectrum, as we move from left to right, through X-rays, then ultraviolet, the colors of the rainbow, infrared and microwave radiation, then radio waves, the increasing wavelength results in decreasing energy. The opposite is true when we go the other direction. Shorter wavelengths result in increasing energy. So what's the connection between UV radiation and ozone? Quite simply, UV radiation is responsible for creating ozone. When ultraviolet radiation strikes oxygen molecules, O2, that causes those oxygen molecules to break apart into individual oxygen atoms. Because atomic oxygen is highly reactive, a single oxygen atom reacts with a different oxygen molecule to form O3. Ozone formation is also accompanied by a release of heat. You may recall from a much earlier unit that the stratosphere is relatively warm. The absorption of UV radiation occurring in this layer of the atmosphere is responsible for the associated temperature increase at higher altitudes. This model helps to illustrate the cyclical process of ozone formation and destruction. As stated, UV radiation from the sun strikes an oxygen molecule, splitting it into two oxygen atoms, which are then free to combine with another oxygen molecule to form O3. This natural construction and destruction cycle is regularly occurring within the atmosphere and, without human interference, would remain in relative equilibrium. The ozone layer is a requisite for most life on Earth to survive. Not actually a layer, it's really a region about 20 to 30 kilometers up, where ozone is found in its greatest concentration. There, ozone comprises about 10 out of every million atmospheric gas molecules. For perspective, that concentration of ozone would make a stack of molecules about 3 millimeters high if it was condensed into an actual layer. The ozone layer is responsible for blocking the sun's harmful UV radiation from reaching the Earth's surface. The highest energy and most dangerous shortwave UV radiation, UVC, is blocked entirely by ozone molecules. About 90% of the medium wavelength UVB is shielded by the ozone. UVB is most responsible for skin damage ranging from suntans to sunburns, and for leading to the DNA damage that can trigger skin cancer. About half of the long-wave UVA, also called soft UV and black light, passes through the ozone layer. Although less destructive than the relatively higher energy UVB radiation, UVA can still cause damage to skin cells. It is associated with the aging of skin cells, and chronic exposure leads to wrinkles. And UVA is thought to play a role in some types of skin cancer. Here's something interesting to think about. It is UV radiation from the sun that triggers the formation of ozone gas in the Earth's atmosphere. But then, it is that very ozone that blocks much of the UV radiation from making it to the Earth's surface. Vitamin D is formed by a series of biochemical processes in the cells of our lower layers of skin upon exposure to UVB. But relatively higher levels of that vitamin D are connected to lower risk of skin cancer. Exposure to UV radiation is responsible, especially for fair-skinned people, for the production of a protective substance against UV radiation. Earlier, I mentioned that the creation and destruction of ozone are kept in relative equilibrium. Ultraviolet radiation catalyzes its formation, and it's naturally broken down, mainly by compounds in the atmosphere like naturally occurring nitric oxides and hydroxides. But still, that natural create and destroy cycle is kept stable, at least until we get involved. In the middle of the 20th century, after World War II ended, the commercial use of ozone-destroying compounds became more prevalent. These compounds shifted the balance of that equilibrium in favor of ozone destruction. It was being destroyed faster than it could be created. The human-made compound that deserves most of the blame for ozone destruction is a class of molecules called chlorofluorocarbons, or more easily pronounced CFCs. They are named as such because of the atoms that they possess: chlorine, fluorine, and carbon. CFCs were widely used as propellants in aerosol cans, as well as refrigerants in things like air conditioners, and as industrial solvents. The reason why CFCs have their destructive power is because of the chlorine they possess. When a CFC enters the environment and travels through the atmosphere, it can be broken apart by ultraviolet radiation. That ultraviolet radiation liberates a chlorine atom that is then free to attack ozone. It does so by ripping off one of the atoms, destroying that ozone molecule, forming something called hypochlorite. This hypochlorite is very unstable and readily breaks down, freeing the chlorine atom to destroy yet another ozone molecule. The destructive nature of CFCs was first studied in 1973, and by the mid-80s, how damaging it was to the Earth's ozone was widely known. Take a look at the short video produced by National Geographic, linked above, for a great summary of what we've seen so far and an introduction to the Montreal Protocol. The Montreal Protocol is an international treaty that went into effect in 1989. Interestingly, it was the first time in history that such a treaty was universally ratified. Because of that universal ratification and worldwide support for its efforts, it's been widely hailed as a success story in international environmental protection. Although ozone formation is a slow process, the fact that far fewer ozone-destroying compounds are released into the atmosphere has allowed for the healing process to begin. Scientists currently project that by the year 2050 to 2070, ozone concentrations will be returned to their 1980 levels. The need for things like refrigerants and propellants, however, did not disappear with the Montreal Protocol. Compounds called hydrofluorocarbons, HFCs, replaced them because they don't contribute to the destruction of ozone. Like CFCs, however, they are a greenhouse gas, and they do contribute to anthropogenic climate change. So, in order to combat that issue, an amendment to the Montreal Protocol aims to phase out the use of HFCs by the year 2030. And that brings these ozone topics to a close. So thanks for watching. Until next time, take care.